Okay, so
welcome everybody to our Gamma seminar. Today we have the pleasure as Ioan Bucataru from the Faculty of Mathematics of the Alexandru Ioan Cuza University. So, Ioan, thank you for accepting our invitation. And Ioan is going to talk about an introduction to Finsler geometry, an approach using the Frölicher-Nijenhuis formalism, and a comparison with Riemannian geometry. So, once again, thank you for accepting our invitation, and the floor is yours.
okay, thank you very much for the invitation. So what I will try to explain today is how Riemannian geometry evolved from how Finsler geometry evolved from the Riemannian geometry. And in order to understand this, I will go back to the origins of the Finsler geometry. So it was somehow in the 19th century when the non-Euclidean geometry was born, so the first non-Euclidean models due to Lobachevsky Bolyai appeared in the 19th century. So they came with this very interesting idea that actually the way we measure it's up to us. Yeah. So up to let's say, 19th century. So the Euclidean geometry, people using Euclidean geometry were using the Euclidean distance. So something that came with the geometry. So it was the idea of actually Riemann who said that actually we decide how to measure. So if you want to measure what you actually need, first to measure the length of a curve, you need this uh, element, arc element ds, which is a function of x position and the direction. So this is what you need. So something very, very general, a non-quadratic, still one homogeneous function, as I put here, ds, function of x and dx. So because this idea of Riemann somehow was quite controversial over time, here I quoted the exact statement of Riemann. So he said that in full generality, the magnitude of the line element can be expressed by this function of x and dx, which depends on position and the direction, not on the magnitude. So this is the reason why this function is one homogeneous in the dx element. And he said that, however, this general problem of representing the length of a line element by such a function is not easy approachable. So he was already aware that by that time it was not easy to study this problem. So this is actually the reason why he said that he will consider only the case in which the magnitude is determined by a quadratic form. So actually, this function here, f of x and dx, depends, is quadratic on dx. Yeah, or you can
Sorry,
see here. Yeah.
Sorry, Ioan, maybe this was from his habilitation thesis or something like that, because I
Yeah.
think that I have heard this before, yeah?
Yes, exactly. So it's from his habilitation thesis, as I said here.
Yeah, sorry, I didn't notice, yeah.
Okay, so this idea was presented in his habilitation thesis. What I quote here is a translation that appeared later on. So this quotes here the English expression of, well, translation of his quotes are from this paper, from this book. But exactly, these are his words from his habilitation thesis. Now I wanted to quote exactly his words, and I could find, because I don't read German, so I was looking for some English translation. Okay, so and these are from this paper from 1953. Okay, so going back, Riemann decided to study only this kind of line element. The very general situation was studied almost 50 years later by Paul Finsler in his thesis. It was in 1918, his dissertation on curves and surfaces in general spaces. And these general spaces were using already this very general line element. However, this thesis was not published, and his work was not so well known until 1934, when Élie Cartan, actually, he published a book which he called Les Espaces de Finsler in French, and where he actually introduced the term Finsler spaces. Again, the thesis of Paul Finsler was not known, and it became, so it was published later on in 1951 in French, in German, and this was popularized by Busemann in 1952. So starting with the work of Élie Cartan, actually Finsler spaces started to become more popular. So here I quote only few works on Finsler geometry that are very famous. So it is this paper of Stern in 1996, published in Notices of the American Mathematical Society, where actually he says that, he states, it is the title of his article, that Finsler geometry is just Riemannian geometry without the quadratic restriction. So somehow it looks like it's very easy to extend Riemannian geometry, so, or results of Riemannian geometry from the to the Finslerian context. You just give up the quadratic restriction and you get. Well, it's not so easy, because when you give up this quadratic restriction, what most of the problems that are quadratic or in the sometimes linear in the Riemannian context, in the Finslerian context they are non-linear, and the non-linearity is not very easy to deal with. Okay, another paper, another book that is fundamental for Finsler geometry is this book by Bao, Chern, and Shen, An Introduction to Riemann and Finsler Geometry. And in this book, they actually present very nicely the translation of very important problems from the Riemannian context to the Finslerian context. Here I'm quoting another recent paper. Actually, the paper is not very recent, so it's circulated for many years, and it was not published until recently, where Riccardo Gallego Torome, what he does is, if you take a Finsler metric, you take somehow an average in the direction, and you get a Riemannian metric. However, not all the properties of the Finslerian metric translate to this Riemannian metric. So it is not easy to study the Finsler metric, properties of the Finsler metric, using the Riemannian metric. Okay, so these are more or less about history of the Finsler geometry. Let me say briefly what a Finsler metric is, and then I will continue with some ideas how to study some problems in the Finslerian context. So we do have a Riemannian, a manifold, an m-dimensional manifold, where local coordinates are denoted by x. And I will consider Tm the union of the tangent bundle, the union of all these tangent spaces. It is a 2m dimensional manifold with local coordinates x and y. Think to this Tm as a foliated manifold where the leaves are tangent spaces. So this way the y coordinates are coordinates in the fibers, in the leaves, and x coordinates are transverse coordinates. So what is a Finsler metric? It is a family of norms, while a Riemannian metric is a family of scalar products in each tangent space. A Finsler matrix is a family of norms, so you have a norm in each tangent space that has some properties. So you need some smoothness. If these norms are smooth everywhere except the zero section and continuous everywhere, we still have this homogeneity but only positive homogeneity. So, and we have this non-degeneracy here. Sometimes some people will ask for positive definiteness. Usually I don't need positive definiteness. So I will use only the non-degenerate situation. So Finsler metric is a collection of norms that satisfy these properties. Of course, when we have a Riemannian metric, if we take the norm induced by the Riemannian metric, we get a Finsler manifold. So a Finsler metric that is induced by a Riemannian metric. Okay, so before I will go, as I said, I will try to study Finsler manifolds with the help of Frölicher-Nijenhuis formalism. So one of the problems that appear in Finsler geometry is that Finsler geometry deals with lots of tensorial quantities that are not easy to deal with. So what I was trying to avoid is to use these tensorial quantities, so this use of indices, and to obtain a global approach. And in order to obtain this, I will use this Frölicher-Nijenhuis formalism. And because I'm not sure how familiar are people with the Frölicher-Nijenhuis formalism, so I will try to make a very short introduction to the Frölicher-Nijenhuis formalism. So very briefly, the Frölicher-Nijenhuis formalism, it is the theory of derivation associated to vector valued forms, and the commutator of this derivation actually defines the Frölicher-Nijenhuis bracket. So let me explain a little bit more this association. So we know that a vector field on a manifold, so by x round of M here, I denote the set of vector fields on the manifold. So we know that a vector field on a manifold, it is well determined by its action as a Lie derivation. So if you have a vector field, you can consider the Lie derivation in the direction of the vector field. But also you can recover the vector field from a derivation on the algebra of smooth functions. Because on the space of derivation of smooth functions, we can consider the Lie algebra structure. So it means you add the derivation, you multiply with real numbers, and you can consider here it's the commutator of two derivations. So do you see when I move
yeah, we should. Yeah,
okay?
we should.
Okay.
Yeah, it's fine.
Okay, so if you consider the set of derivations with this, here is the commutator. This commutator here, with this isomorphism here, you can move the commutator on the commutator of vector fields, and we get actually the Lie bracket. So the Lie bracket can be taught like that. So the Lie derivation corresponding to the Lie bracket corresponds to the commutator of the Lie derivation. So this is a very nice idea that actually can be extended to any derivation. So here these are derivations of degree 0 on smooth functions, but this derivation can actually be extended to derivations of degree 0 on, this is the space of forms of degree k. So let's move further and explain what a derivation of arbitrary degree is. So this is the set of integers. So a derivation of degree R is an integer, is a map that takes k forms into k plus R forms. Yeah, so it increases the degree of the form by R if R is positive, or decreases if R is negative. That is linear, so the derivations are linear functions, linear maps. It satisfies these Leibniz rules, derivations of the wedge product. So the product here is the wedge product. It satisfies this rule here. It's a graded Leibniz rule. And of course, you need this local property of the derivation. So we know what derivations of degree are satisfy this three property. So on the set of derivation on forms, we can consider this commutator. This commutator actually satisfies this graded skew commutativity. It satisfies this graded Jacobi identity. Think to this as a Jacobi identity, but it takes, well, into account the degree of this derivation. With this commutator defined here, so we have a graded Lie algebra. So the idea is to transfer this graded Lie algebra to vector-valued forms. So to associate to these derivations, to associate a vector-valued form, and to transfer this structure of graded Lie algebra to vector-valued forms. So here I gave you some examples of derivations. So the usual inner product with a vector field is a derivation of degree -1. The Lie derivation is a derivation of degree 0. The differential, the exterior derivative, is a derivation of degree 1. They do satisfy, so if you take this commutator here in this sense, you get Cartan's formula. Okay, so how to associate, yes.
Ioan, may I have just a comment, because we teach students these things during the differential geometry on our second, third year, and they are very useful to remember, for example, the signs for the Cartan's formula. And by the way, it's another example is the contraction with the Lie bracket, like the commutator of the contraction of a vector field with the Lie derivative. Yeah, for example, it's another one of these.
Yes, sure. I will come back to that as well. I just gave an example. Yes.
Thank you. Great.
Yeah, and of course this commutation here, but I will give you, I can present that as well. Okay, so the idea again is to associate to these derivations, to the set of derivation on space of forms, the space of vector-valued forms. Yeah, how to do this? So because of this Leibniz property here, any derivation is well determined by its action on zero forms, so scalar forms which are functions, and one forms. A very simple observation is that derivations, because we don't have forms of negative order, it is very simple to obtain that derivations of degree less than -2 are trivial. And I have denoted here by psi k of m the set of vector-valued k forms. Yeah, so are maps that take k vectors into a vector field, and it is skew-symmetric. Yeah. Again, I recalled here that derivations on set of functions can be identified with vector fields, which are scalar vector-valued forms. And what I will try to explain next, how to associate to a derivation on forms a vector-valued form. Yeah, and the commutator here will correspond to what is known as the Frölicher-Nijenhuis bracket of two vector-valued forms. Okay, so what is important, again, as I said here, derivations are determined by their action on functions and one forms. There are two important derivations. One that are trivial on functions, and therefore, because they are well determined on functions, and one forms, because they are trivial on functions, they are uniquely determined on one forms. These derivations are called algebraic derivations. You will see why algebraic, or sometimes I-star derivation. What I presented here is an example of such derivations, but you will see later that these are the only derivations of this type. So if we have an vector valued L form, we can define this derivation of degree L minus 1. Yeah, so it increases the degree of forms by L minus 1. Here is the exact expression, but it is easier to think as I put it here. So IL omega, it is just omega of L and all its arguments here and all other arguments. So if you take omega of L and everything that you can put there, you may not have K plus L minus 1 form. So what you do, you take the alternation of this tensor and you correct it with this term here because of the Leibniz rule. So this correction here is the correction that sometimes people use it for when you define the wedge product, sometimes don't use it. I do use it. So in my case, the wedge product is just is given by the determinant rule. Okay, so this is a derivation of, it is a derivation in the sense of the definition that I presented above, of derivation of degree L minus 1. Some examples. When omega is a 1 form, then IL omega is just the composition with, so if omega is a 1 form, this quantity here, EIL omega, is a derivation of degree L minus 1 because this quantity here, it's an L form. Omega was a 1 form. I add L minus 1 and omega composed with capital L is an L form. Another important property, if I take this derivation with the identity viewed as a vector valued 1 form, what we get is this nice expression here. So it is, we just multiply omega. Identity is a 1 form. The derivation, this derivation here is a 1 minus 1 derivation. So it's a derivation of degree 0. So it keeps omega. So it takes omega into something proportional with omega. So it gives omega, associate omega with K form. If X is a 0 vector valued form, so it's a vector field, then this is the usual inner product. Okay, so these are algebraic derivations. So there is another type of derivation, so what are called the Lie derivation or D-star derivation. And they are well determined by this property here, commutes with the exterior derivative, and because it commutes with the exterior derivative, they are well determined by the action on smooth functions, because on one forms with this commutation with the exterior derivative, they are well determined. If I know them on functions, I know them on one forms, and then I know them everywhere. And here again, I gave an example of some Lie derivation. If I have a vector valued form, then we can define this DL, this Lie derivation, in the following sense. It is precisely the commutator of IL that I just defined, and this exterior derivative. It is this commutator. It is a derivation of degree L, small l, And again, here I gave some example. If L is a zero vector valued form, so it's a vector field, dl, it is precisely the Lie derivative along the vector field. And this formula here above, with this formula here above, we recover the Cartan's formula. In the particular case when L is the identity, the vector valued one form, which is the identity, we recover the classical exterior derivative. Okay, now let me make the connection between these derivations of degree R and vector valued form. So far, I gave you examples of derivations induced by vector valued forms. So algebraic derivation and Lie derivations. So the fundamental theorem of Frölicher-Nijenhuis actually it tells that if I have an algebraic derivation, any algebraic derivation is of this form. So there is nothing else. Any Lie derivation is of this form. And more than that, any derivation of degree k actually decomposes into an exterior Lie derivation and an algebraic derivation of corresponding degrees. Yeah. So if D is a derivation of degree k, this is an Lie derivation of induced by a vector valued k form and an algebraic derivation induced by a vector valued exactly k minus 1. Sorry, here is k plus 1 because this has to be a derivation of degree k. Anyway, derivations of are induced by vector valued forms. So what we do now, we take similarly as we did for vector fields. We take two vector valued forms, one of degree k, one of degree L, and we define this commutator here. We consider this commutator here. dk is a derivation of small k, dl is a derivation of small l. Their commutator is a derivation, a Lie derivation of degree k plus 1, k plus l. According to the fundamental form, it corresponds to a k plus l form. This k plus l form is denoted like that, and it is called the Frölicher-Nijenhuis bracket. So, and this is the formula actually that connects the commutator of the derivations with the derivation of the Frölicher-Nijenhuis bracket. And with this, actually, we can transfer the graded Lie algebra of the set of derivations on forms to the set of vector valued forms. And yes, Javier, I thought that I might have the formula that you said here, but I don't have it. I can put it that. Okay. So somehow I had it in mind, but I don't have it now. Yes, but you can recover that formula as well between the inner.
I see that it is quite natural. Thank you. It's great. It's very clear.
Okay. So if we have this Frölicher-Nijenhuis bracket, we can consider the Frölicher-Nijenhuis bracket of a vector valued one form and itself. And this way we get what is called the Nijenhuis torsion. But what is important is that if we take the first one here, a vector field, the Frölicher-Nijenhuis bracket of a vector field and vector valued form, it is precisely the Lie derivative. Yeah, this Lie derivative, you can define it independent of this, but it is exactly this, the Lie derivative. Okay, so once we have this, so here are some references for the Frölicher-Nijenhuis formalists of the original work of Frölicher and Nijenhuis, the book of Kolar, Mihor, and Slovak natural operations in differential geometry, and a book of Griffon and Zoltán Musnay, where they use this Frölicher-Nijenhuis formalism to study the variational principles for second-order differential equations. Okay, so having this Frölicher-Nijenhuis formalism, I will try to go back to the Finsler geometry and study some of the problems in Finsler geometry. So again, I have an m-dimensional manifold, again with local coordinates, its tangent bundle, and sometimes I will use this slash tangent bundle, so the tangent bundle with the zero section removed because of smoothness problems. Some of the problems are not smooth along the zero section. Okay, on this tangent bundle, there are two important structures that I will use. These tangent structures that I called here by calligraphic T or tau, it takes, if you look, as I said here, the tangent bundle, you can view it as a foliated manifold with tangent spaces that are leaves. And if you take the tangent space to this tangent bundle, so the tangent space along these leaves, along these tangent spaces are called vertical spaces. So this tangent structure here actually takes verticals into zero, so ignores the vertical vectors, and takes transverse vectors into vertical. It has this important property, so this is why it is called tangent structure. The square is zero, and it is integrable. So its local expression here allows that its Nijenhuis torsion vanishes, and this integrability is easy to see it from here. Okay. But what is important is that because we have this vector valued one form, so the corresponding derivation has this property. So actually, you can use this as a derivation, and you have a Poincaré type Poincaré type lemma. So because of this property here, so think to this as d squared. So think to the exterior derivative, classical exterior derivative. You have the Ram cohomology. You have all these properties. So you have that closed exact forms are closed locally. Closed forms are exact forms. Something like that you can do for this derivation here. I will use it. Well, we also have this Liouville vector field, radial vector field, with some properties. The bracket with the tangent structure is zero. And this Liouville vector field is very important. In Finsler geometry, although we lose the quadratic property, as Cherps said, we still keep homogeneity. So homogeneous objects in Finsler geometry are very important. So we want to characterize homogeneous quantities. So we'll use this Euler theorem to characterize any object is a tensor is homogeneous of order p is an integer, if satisfies this property. So if you look here, so because I said before that this Frölicher-Nijenhuis bracket, it is actually the Lilly derivative of tau of the tangent structure with respect to the Liouville vector field. This equation here, it tells that tau is zero homogeneous. Okay, now let's formulate some problems in Finsler geometry. So again, we have a Finsler metric. A Finsler metric is a collection of norms. If I have the norms, I can consider this energy. So the square of the norm with this 1/2 in front, just for the sake of keeping the convention with the Finslerists, with the physicians that this plays the role of kinetic energy. Without them, I didn't put any mass here. But if you think to this one as some mass, here it has the role of kinetic energy. So if we take the variational problem for this energy, so if we take the variational problem for this quantity here, what we get are the so-called Euler-Lagrange equations. So the Euler-Lagrange equations are written here. Think to this S here as the vector field along the solutions of the geodesics. So here, think to this d by dt. So the derivatives d by dt. So if you want to see the Euler-Lagrange equation in their standard form, put d by dt here. Y is x dot. So you have Euler-Lagrange equations here. But what I'm trying here to do is not to use this local expression. So the global expression of the Euler-Lagrange equations are a global expression of this Euler-Lagrange equation is written here. It is the Lie derivative of this one form. So I said previously that I will use quite extensively this derivation along the tangent structure, which can be written into this form. By the way, I will, at some point, I will come back to this so d tau e is a one form, d tau e is a two form, and actually it is a symplectic form associated to this Finsler metric. So this is another expression. If you think to E as a Hamiltonian function, you may think to this as Jacobi-Hamilton equations. But I will not use this expression. Anyway, what I wanted to say is that the variational problem for Finslerian energy gives rise to this Euler-Lagrange equation into this form. So for me, this form is very important. Let's, just to make sure that you can view this equation and that it's easy to understand this equation, let's see what happens in the Riemannian context. So the Riemannian context is when this form here is induced by a Riemannian metric. So if this F here is the norm induced by a Riemannian metric, in this case, the energy is this quantity here. And if you if you perform the Euler-Lagrange equation, you get these geodesic equations here. This geodesic equation actually gives you the standard geodesic equation. These functions here are quadratic in dx by dt. In the Finslerian case, you lose the quadratic property. Here, you have the quadratic property. So you see here, these are geodesic equations. So because these matrix here are invertible, you have this. And let me go back a little bit here. As I said, in the definition of the Finsler metric, I require that this quantity here is non-degenerate. I don't need positive definiteness because non-degeneracy here just requires that you have this quantity zero, so classic geodesic equations. A little bit more here. So at some point, I will be interested in the inverse problem. So again here, if I have the Finslerian norm, I perform the variational equation and I get the geodesic equations, which are a system of second-order differential equation. Sometimes I will be interested in the inverse problem. I have the system of second-order differential equation, and I want to see if they are induced by a Finslerian metric. In the Riemannian context, so I have the geodesic I have these equations. Geodesic space means this set of functions which are the Levi-Civita connections. And I want to see if they are induced by a parallel transport which consists of isometries. Yeah. Okay. Again, I have a Finslerian metric, I have this geodesic, this Euler-Lagrange equation, and I want to study them. If I want to study them, if you see here, so the first question you may ask, I have these derivations, the Lie derivative along the geodesic spray, the derivations induced by the tangent structure. So the first thing I can ask is to study the commutator of these two derivations. If I consider the commutator of these derivations, according to the Frölicher-Nijenhuis theory, this corresponds to the derivation of the commutator of these two quantities, yeah, a vector field and one form. This quantity here, it is precisely, so this is a vector valued one form, and actually it has two important properties. I wrote it here locally, but it is important to see that it has just two eigenvalues. One is 1 and one is -1. And corresponding to 1, I have a vector valued, corresponding to 1, I have an eigenspace, which corresponds to the vertical subspace. And corresponding to -1, I have another subspace, which is actually, which I will call the horizontal distribution. And this is how actually we come with what is called the nonlinear connection, which is called sometimes the Ehresmann connection. And we come with this projector here, H, which gives, it is a vector valued one form, it gives the horizontal distribution, and the Nijenhuis torsion of this projector here, it gives what is called the curvature. So in Finsler geometry, we can introduce the curvature. It is nonlinear. We can introduce the curvature as the Nijenhuis torsion of this projector, which is projector in the sense of linear algebra. It's square itself, and then we can define its image as here it is a subspace, it is supplementary to the its kernel, and so on. So using the Frölicher-Nijenhuis formalism, we can define the curvature, lots of properties that by the way, in the Riemannian context, the curvature, this quantity here is one homogeneous. In the Riemannian context, it is linear. And it is this quantity here, it is precisely the curvature of the Levi-Civita connection. We can recover lots of properties using the Frölicher-Nijenhuis formalism. For example, for the this curvature here, you can write the Bianchi identities, algebraic Bianchi identities, differential Bianchi identities. For example, the differential, here I put the differential Bianchi identities, come, if you write the graded Jacobi identity, you get this. This is precisely, it gives you the Bianchi identities for this curvature quantity. So this, in this slide, I just wanted to show you that very briefly, using the Frölicher-Nijenhuis formalism, you can recover lots of properties that extend the Riemannian properties. Okay, I want to go to problems that, how to extend problems from the Riemannian context to the Finslerian context. One problem is related to what is called in the Finslerian context the sectional flag curvature. In the Riemannian context, if you have a Riemannian metric, you can define the Levi-Civita connection, the curvature, and once you have the curvature, you can define the sectional curvature. So the sectional curvature at a point in to the direction of a plane generated by, here is the bivector x and y is the bivector that actually generates the two plane. So the sectional curvature at a point into the direction generated by these two vectors is defined in this classical way. Yeah, so this is the 0,4 curvature. Yeah. In the Finslerian case, things are a little bit complicated because of this. Everything depends on the direction. So if you fix a point, you are forced to consider the direction at that point as well. So this is the reason that in Finsler geometry we have what is called sectional flag curvature. So you have a point and you have the flagpole. This flag here stands for, at each point x, I fix an y, a direction, and then I consider the plane generated by y and x. So we defined the flag curvature at each xy in Tm and in the direction of this two plane in this way. Okay, in the Riemannian geometry, we define the isotropy in this way. The sectional curvature does not depend on the two plane. In the Finslerian context, we already have the direction on this small y here. So we said that we have the isotropy if the sectional curvature does not depend on the flag. We still have the flagpole, but it does not depend on the flag. Okay, so let me go to some problems that I know that do I still have 10 minutes?
Yeah.
Okay, thanks. So let me go to some concrete problems. As I said, also in the Riemannian context, you may ask the following problem. You have a connection, a linear connection, and we want to study if that connection is the Levi-Civita connection of some Riemannian metric. Yeah. If you have the metric, you just test, as I put it here at the bottom of the slide. So a linear connection nabla is the Levi-Civita connection of some Riemannian metric if and only if, yeah, we have this, the covariant derivative of the metric is constant. Yeah, so we have this expression here. You may ask, what is this expression here? Well, let me explain. So I will go back to the Finsler geometry. So I have a second system of second order differential equations. That means a spray. And I want to find out if that spray is the geodesic spray of some Finsler metric. So in other words, I want to find out if there is a Finsler metric, that means its energy, that satisfies this Euler-Lagrange equation. In a very recent paper with my colleague Ioana Constantinescu, we actually answer to this problem in the following sense. A spray S is the geodesic spray of some Finsler structure F if and only if its metric tensor is covariant constant in the direction of the geodesic spray. So this nabla here is not, it is a covariant derivative, but only in the direction of the geodesic spray. In the Finslerian case, while in the Riemannian case, you have for each metric one important connection, Levi-Civita connection, symmetric and covariant constant. In the Finslerian context, there are more connections. Some of them are metric, some of them are not metric, some of them are symmetric, some of them are not symmetric, and so on. So I didn't want to go here into all this detail. However, all these connections, they coincide when you consider the connection along the geodesic spray. So here, this nabla here, it is a covariant derivative along the geodesic spray. So this is why we have this covariant derivative in the direction of the y. Okay. In the Riemannian case, this covariant derivative in the direction of the geodesic spray is linear. Because this quantity here is linear in the Riemannian case, you can just drop this y and you recover what is known in the Riemannian context. Okay, so this was one of the problems that we actually solved. We extended what is known in the Riemannian case to the Finslerian case, and we truly used this quantity here is not linear, and we did use the Frölicher-Nijenhuis formalism. Okay, so this was somehow the inverse problem for the variational problem of the energy. What about the variational problem for the Finslerian norm? So if we perform the variational problem for the Finslerian norm, we obtain again the Euler-Lagrange equation for the Finslerian norm. However, these Euler-Lagrange equations here, they do not give us uniquely the geodesic spray, one spray or one set of second order differential equations. So what happens here is that this Hessian here of the Finslerian norm is it is degenerate. It has actually the rank n-1. Because it has the rank n-1, it does not have the maximal rank. This system here this system does not uniquely give us one spray. It actually gives all the sprays that are projectively related. So it gives all the system of differential equations with the parameter not fixed. So if you have a system of second order differential equation, if you change the parametrization, you change the system. You have a new geometry, actually. However, in this case, changing the parametrization does not change this system. It changes the geodesic spray, but it does not change this system. You get a full family of geodesic sprays. Okay. What about the inverse problem? What is called the projective metrizability problem. You have a spray, and with that spray, you consider the full set of projectively related sprays. The question is that, is this spray projectively related to some Finsler metric? So I studied this problem with Zoltan Muzhnai almost 15 years ago. And we did use the Cartan-Keller theory, and we started this problem here, and we came up with this system. I want to finish as soon as possible, so I will go quite briefly here.
Ioan, listen, normally we always finish after the time, so don't worry, you still have time to explain this. And indeed, I have a couple of questions. Well, maybe I can make them at the very end. But I am all the time thinking, okay, Finsler geometry is more general, that's Riemannian metrics and things like that, the Riemannian geometries. But how much is this general? I mean, for instance, for the inverse problem, yeah, you have an inverse problem to describe it by means of Riemannian geometry, and here you have Finsler geometry. How much is general? Do you have any example of a second order differential equation describe that it's not cannot be recovered in the Riemannian setting, but it can be recovered in the Finsler setting, and it has some applications, so it has some properties, for example, in physics. Do you have any of these things?
Example of what more exactly?
A problem that it has not an inverse problems in the Riemannian setting, but it has in the Finsler metric. And it's something that it can be used to study physical problems or mathematical problems with something not academical, something with application. Could you comment on that?
Yes, maybe I should go to another problem. Okay, I will give examples quite soon. Yeah. Okay.
Okay.
Now, I'm not sure if the answer to your problem, but okay. Very briefly, what happens in the Riemannian context? Very briefly, two results from the Riemannian context that can be extended somehow to the Finslerian context. So Schur Lemma tells us that if you have a Riemannian manifold of isotropic curvature, so that means the sectional curvature does not depend on the direction of the two planes, actually that sectional curvature is actually constant. And it uses differential Bianchi identities. Another important result from the Riemannian geometry is this Beltrami Theorem. If you have two Riemannian metrics that have the same geodesics up to reparametrization, and one is of constant curvature, the other one is of constant curvature as well. So actually, you cannot have projectively related Riemannian manifolds, one of constant curvature and the other one of non-constant curvature. And here, a few years ago, I tried to extend this result with one of my former PhD students, Georgeta Crețu. So in Finsler geometry, here I said I'm not sure if these are the examples that you were looking for. In Finsler geometry, there are examples of Finsler metrics of non-constant flag curvature that truly depend on the direction. So the isotropic condition itself is not enough to use Schur's lemma. And because I want to go to the Beltrami theorem, there are examples of projectively related Finsler metrics that have the same geodesics. So by reparametrization, you move from one to another one, but one is of constant curvature, the other one is not of constant curvature. Yeah. And what is important, so here is the theorem that I said, what is important is that even if you take a Riemannian metric of constant curvature, in the Riemannian context, this deformation by reparametrization, this deformation of the geometry by reparametrization, you can see this into the geodesic spray, into the vertical part of the geodesic spray in terms of some projective deformation that is some function. In the Riemannian case, this quantity here, this function is linear. It corresponds to some gradient function, and it is very simple. In the Finslerian case, this is very, very general. So there are examples of Finslerian metrics that do not satisfy this quantity because this function P is very general. However, what we managed to prove is that if I have two Finslerian metrics that have projectively equivalent geodesics, and they are both of constant curvature, if and only if this this projective deformation, this function here, it is of some particular form, which in the Riemannian case, it is automatically satisfied because of the particular form of the projective deformation. Okay, I'm not sure I did answer to your question, Javier. So again.
A little bit, yes.
Okay, thank you. And I will try to go a little bit further. Another problem, very important, when you deal with geodesics. Geodesics are given by a system of second-order differential equations that are very hard to integrate sometimes. So you cannot actually have explicit form. You don't really know how the geodesics look like. So what you want qualitative informations about the geodesics. Well, more important, you want, if possible, to integrate this geodesic equation. In the Riemannian case, it is known that if you have a system of a Riemannian metric with the corresponding system of differential equations, and by some projective deformations, by reparametrizing, you get to a new system that again is a system of geodesics, then that solves actually the problem. You can integrate, because if that means that the original system of geodesics and the other system of geodesics are projectively related, and in the Riemannian case, if two projectively related Riemannian metrics need a system of first integrals, then you can integrate. And this is true because if two projectively related Riemannian metrics, two projectively Riemannian metrics, for two projectively Riemannian metrics, you can actually compute a system, you can find a system of independent first integrals that commute, Poisson commute. Well, this is something done by Tabachnikov using geodesically invariant volume forms. There is another technique that developed by Vladimir Matveyev and Bolsimov. They use something different. So I tried to extend this technique to the Finslerian case, and I did it with my colleagues Oana Constantinescu and Giordeta Crețu. So what I did is, if I have a Finsler structure, I can construct this sphere bundle. So I consider only a submanifold on Tm of norm 1. So I consider only those directions of norm 1. This together with this Hilbert-1 form and the corresponding normalized geodesic field, it is a contact manifold. On this contact manifold, if you consider the corresponding volume form, you get something that is geodesically invariant. If you consider a projectively related Finsler metric, you get again some geodesically invariant quantities, volume forms. Because they are volume forms, they are proportional. And because the volume forms are geodesically invariant, the proportional factor is geodesically invariant. And this is how actually I came up with only m-1 first integrals. There is another one, but I will not go into those. The only thing I was able to do is to find these first integrals. I don't know if they commute, so I don't know if they are helpful to obtain complete integrabilities. Okay, so sorry, Javier, can you say again the question, because I'm not sure I did answer.
Yes, it's okay. I was wondering how much this Finsler geometry is general with respect to Riemannian geometry. I will explain what is the point. For example, in many cases, the typical example is Riemannian of Riemannian geometry, yeah? And in general, for example, in tangent space to every point, you have a norm. But I would have wanted to see some, let us say, example that is not the Riemannian one, and where the norm has some particular shape, some case
yes.
of Finsler geometry, that it is Finsler geometry that is not so much related to Riemannian geometry, to see whether they have this was my one of the things I was interested in, one of the questions, because with Riemannian geometry, more or less, I could feel how everything has to be generalized, and it's very helpful. But I would like to see how it differs from the Riemannian
If you
case.
do have time, yes, I can, but I have to write it down. I will connect my tablet, and
Okay,
it
go
depends
ahead,
on
please. Because,
how much. Okay, let me
by the way,
start.
Tom wants to say something. I don't know if maybe after.
Yes, Tom, please.
Well, if you are connecting your laptop anyway, I can already give an example, Javier. Maybe.
Oh, great.
Okay.
Yeah.
Because you were referring to this in the context of the inverse problem that Ioan was showing. And you can think of the following, think of the Poincaré disk. And then you know that the geodesics are perpendicular to the bordering circle.
Yeah.
Right? But the horocycles, they're also circles which are tangent to the border circle. So you could ask yourself the question whether these horocycles, maybe they are also geodesics for some metric. And then you can show that, well, it does not exist a Riemannian metric for which the horocycles are geodesic, but there is a Finsler metric.
Yeah, this is a good example. Okay, thank you.
Yeah, so that I think that sort of answers, goes in the direction
Yeah,
of the...
it sounds
Yes.
that.
I was prepared actually to write down a Finsler metric for you. And this is can you see what I'm writing?
Yeah, sure. Go ahead.
And this is related to what is called Zermelo navigation.
Okay.
Did
yes,
you hear
I heard
me?
of that.
Okay, so think you have a Riemannian metric and you have a vector field, a wind. And what you want is, so originally, this is the indicatrix. So this is what we call in the indicatrix. So the sphere for this norm, yeah? But if the wind blows, this, and it is centered at x, yeah? If the wind blows, you will have something similar. It is still a sphere, but it is centered here.
Sure.
Yeah, but it's not difficult to derive that, to show that this is what is usually called the indicatrix of G.
Yeah, sure.
And this will be the indicatrix of some Finsler function. And it is very easy to actually to derive this. So what happens, look, what is the connection between these two? So here I have, let's say, y in yg. It implies that y plus w belongs to yf. Yeah. So it takes this wind, it takes this sphere here, the Riemannian sphere, into the Finslerian sphere. But think a little bit different. I want to derive f. So take y arbitrary in Txm with some f which I don't have yet. Y over f will belong to the indicatrix, yeah? That means y over f minus g, minus w belongs to this.
Yeah, it's,
that
I know
means
where you're
that
going.
norm over y over f minus f is 1. If you solve this equation, you get f. And f can be written, it has a very nice form. Actually, it is something 1 minus norm over w squared, some square here. It may look that it's complicated, but it's not complicated. So this is a purely Finslerian metric.
Okay, wonderful. That's what I was thinking of. Yeah, because sure. I was looking for something like that, to have some typical example. Let us say this matter that is not Euclidean. So thank you.
Yeah. No, so this is typical. Yeah.
Yeah. Is there any other question?
Sorry?
I was asking whether is there any other question from the audience? No. But I have another question, last question to finish, because you have been describing how this differential and the Frölicher-Nijenhuis structure and the Finsler geometry appear related to contact geometry. How much is this developed, and how many other structures are related to this Finsler geometry? Symplectic, Hamilton, and Jacobi, which...
Yes, you do have also, you can use, you have a symplectic structure So you have Tm with d tau e. This is a symplectic manifold.
Okay.
You have also a Sasaki type matrix, so you do have also Tm with some metric G and d tau e. This is an almost Kählerian manifold.
Okay.
So you have contact manifold.
There is plenty, yeah. There's plenty of
there is also an almost complex structure here. And all of them, what is very nice, all of them can be introduced with this, well, they can be introduced locally, but they can also be introduced with this Frölicher-Nijenhuis formalism. Yeah, so there is Kähler structure, almost Kähler structure, yes, because it's not integrated.
And a last question, because when you introduced the Frölicher-Nijenhuis, you did it with vector valued functions, but could you do it, I guess, on vector bundles with vector value forms?
Yes, I'm sure it can be done.
With a connection,
At some point, I tried with Zoltan to extend a little bit more, but not too much.
Okay. So, any other question, remark? No. So, thank you, Ioan, by a very nice talk. It's been very instructive, and for sure it will be very useful for our students. So, thank you very much, and I hope. Please send us the slides if you don't mind.
Yes, I will send it. Yeah,
and I will post them in our web page as normal. Thank you, and well, we will see you, everyone.
Yeah, keep me updated with the next talk, so I might attend some of them.
Yeah, sure. Next week, indeed, we have Alexandro Arce, and we have even the topic. Thank you.
Okay, I will look at.
But yes, we will send you the an email. We can add you to the distribution list. So thank you, everyone, and we will see you now in a week. Bye.
Bye.
Bye, Tom.